In this video, we're going to discuss how to identify linear functions in different representations. So just remember, any relation or function can be represented in different ways. We could see information as a table, we could look at ordered pairs, we could look at them in function notation, we could look at their graphs, or we could look at equations. So we need to be able to look at all different types of forms and determine whether or not our functions are linear. So if we see an equation, we should see something like these guys. There are other forms, but the key thing is that x is only to the first power, so we won't see that. It'll just say x. It'll just say y. We don't want to see any variables in the denominator, things like that. So examples that are not linear would be something where x is raised to a power. Something like that is nonlinear. If we look at something like x in a denominator, that's nonlinear. If we look something at x is under a radical, that is not linear. So x and y are just x and y. They're allowed to have numbers in front of them, but nothing else. Again, these are two very common examples of linear functions. Our functions may not start in this form, but we can always rearrange them. So if we're trying to find if something is linear or not, we can get y by itself. And if it looks like slope-intercept form, it's a linear function. We can always get x and y on the left hand of this equal sign. And if it's in this form, which is called standard form, it is a linear function. There are other forms that we'll talk about later, but again, the key thing is that x and y are just kind of x and y to the first power. If we're looking at graphs, we see that word linear, we see that word line inside the word linear. So we're looking for something that is one straight line. We don't want to see any pointed edges. We don't want to see any curves. So some examples of linear function could look like this. It could go down. It could be horizontal. As long as it is one straight line, it is a linear function. If we look at something that is nonlinear, we may see a curve in it. We may see a sharp point in it. So those are examples of nonlinear functions. If we look at tables, we do need to make sure that our table is set up in a way that we can answer the question. So first, we're going to start by making sure we have a constant change in our x values. If we do, then we can determine what type of function it is. If it's a linear function, it is also going to have a constant change in the y values. And that just means we're going to either be adding or subtracting the same value over and over again. Okay, so in order to answer or to determine what kind of function it is, we always need to make sure that we have a constant change in our x values. And so here we're going up by 1 each time. That means we can use this table to determine what type of function it is. As long as we are increasing or decreasing by the same number each time, then we say this is a linear function. Okay, another example is here to the left, or sorry, to the right. We're adding 2 each time. That means I can determine what kind of function this is. So if we come up here, we're actually going to add 6 over and over again. Because this is a constant change, we say this is linear. Okay, an example is over here on the right. Here, again, we're adding 1 each time. That means I can determine what kind of function this is. But if I look on the right, I'm subtracting 1, and then I begin to add 1. So this is a problem that we don't have a constant change. So this guy is not linear. We can look at another example. Again, our last one here to the right. We have a constant change in x. Okay, so we can look at our y values. Here I'm going up 3. Here I'm going up 5, and here I'm going up 7. So this is not linear. If I'm given a set of ordered pairs, I can actually write it as a table, and then I can go back and use this method again. So what I've done here with these ordered pairs, remember these are x, y ordered pairs. So I've taken each one and I've written them as a table. And again, just make sure you can use the table to determine whether or not it's linear. So make sure you have a constant change here in your x values, and we do. And then we can look at our change in y. And because we are increasing by 1 each time, that means this guy is linear. And if it's a question and we're asked to answer with a sentence, here we would say this is linear because there's a constant change in both x and y. My table disappeared. There you go. Okay.